Right. So a diversity combining technique. So we already now know that diversity has a very important role to play in order to overcome the effect of fading. So as fading is troublesome for us, so we need to have diversity techniques. And then we have to know, and we need to know the diversity combining techniques, right? So how to combine the signal and get the relevant output. So for a slowly flat fading channel, the equivalent low pass of the received signal of the branch I can be written as this, right? So we are looking at the equivalent low pass signal, and that is the received signal from the branch I, since we have multiple branches in case of diversity. So in ith branch, the received signal is AI e power j theta I s of t plus z I t from 0 to m minus 1. That is, m signals are being considered over here. So here S of t is the equivalent low pass of the transmitted signal. So that was a signal that was transmitted, and we want to get this signal, yes. But this is getting multiplied with AI ej theta, that is the fading attenuation relevant to this ith branch. So the signal that was transmitted is getting mixed with the fading attenuation relevant to whatever ith branch is. And then Zi of t is the additive white Gaussian noise. And we know that the Gaussian noise that gets added to the signal is additive white Gaussian noise, having a flat spectrum. So this is the AWGN noise that is getting added with the signal that we were ought to receive, but that is getting uh, mixed with the fading attenuation, right? So since we are considering M channels over here, or the M branches, so out of M branches, M replicas of the transmitted signal are obtained. So we are getting in the form of a vector, you can say R1t, R2t up till Rm minus 1t. So we are getting total of multiple signals. That is not only the R1t, rather we are getting multiple signals, right? And M is the diversity order. M is known as the diversity order. The number of branches, you can say, or the number of channels in this case, or the number of branches, both mean the same. So that is the diversity order. Okay, so we are getting multiple signals at the receiver. So the combining technique in which out of n channels, you select the channel that has the maximum SNR. This type of technique is known as selection combining technique. So this is a transmitter. We have multiple branches or the multiple channels, and we have some SNR monitor. This is sort of a SNR monitor that is monitoring how much SNR is being fed to us by channel 1, how much SNR is being fed to us by channel 2, how much SNR is being fed to us, for example, by channel N. And out of N channels, it will figure out the channel that has the maximum SNR. And this channel that has the maximum SNR, then that would be selected, and that would be obviously processed at the receiver end. This type of combining technique is known as selection combining. This type of selection technique is known as selection combining. The next type of technique that we're going to see is maximal ratio combining. This is significantly different from the selection combining technique. In this technique, you can see that we have a transmitter, we have a number of channels, and after each channel, we have some weights associated with each channel. And then we combine them as we are summing them, and that is being fed to the receiver. So let me tell you, in maximal ratio combining technique, it is a signal processing technique used in the wireless communication to improve the signal to noise ratio. Yes. It involves combining multiple received signal, each with their own SNR, in such a way that the resulting output signal has maximum possible SNR. So it's not that we are selecting the channel which has the maximum SNR. We are trying to gain as much as possible from each of the channel, and we are trying to increase the SNR even beyond the maximum SNR that an individual channel may have, right? So Here we are combining the received signals. Each of them have their own SNR. We are combining them in such a way that the resulting output signal has the maximum possible SNR. This is achieved by weighting each received signal proportionally to its SNR before adding them together. So this is achieved by weighting each received signal proportionally to its SNR before adding them together. So maximal ratio combining is particularly effective in diversity reception systems where multiple antennas receive the same signal with different fading characteristics. So this is quite useful for these kinds of applications. So this is a second type of combining technique that we saw. The next type of technique is equal gain combining. This is the third type of combining technique. Coherent combining of all branches with equal gain. So this is actually the coherent combining of all branches with the equal gain. And it is also sometimes considered a simplified version of the maximal ratio combining. So what the basic concept is, each branch signal is rotated by e power minus theta I, and all branch signals are then added, right? So let me tell you the detail of that. So in equal gain combining, it is a type of diversity combining where the signals received from different paths are combined in such a way that each signal path is given an equal weight or gain. So you just saw that we have different weights in maximal ratio combining, but here we are giving equal weights or gain. So unlike other combining methods, equal gain combining does not prioritize any specific path based on the signal strength or quality. So how the process of combining works basically, the signals from the each path are first co-phased, meaning that their phases are aligned, then they are added together. Since each path is given equal importance, this method is simpler to implement compared to the maximum ratio combining, which gives different weights based on the signal strength. So you can say that it has almost the same type of structure as the maximal ratio combining. Instead of this, that each of the branch is given equal weight. So that is sort of a co-phasing. All of the branches are first co-phased. That is, the phase of each of the branch is aligned, right? So this is very important. So you can say that the combiner output is e power minus j theta I r I t from I equal to 1 to m. And similarly, we are opening this r as a, s, and then this thing. This is basically the same equation that we have seen earlier. So you can say that this is a much simplified version of the maximal ratio combining. And the SNR is given by this expression. Obviously, this is derived, but this is how it works. Okay. The next thing is the switch diversity combining. When the signal quality of the used branch is good, there is no need to look for the other branches. So this is switch diversity combining. You don't need to look at other branch if you just see some branch and you feel that the branch is okay or the quality of the signal is good, you don't need to look at the other branches, because the other branches are only needed when the signal quality deteriorates. For example, just look at the selection combining. For example, you monitor the SNR of the channel 1, then you don't need to monitor the SNR of the channel 2 if the quality of the or the SNR of the channel 1 is beyond, you can say, a certain threshold. You say that the quality is okay, I'm okay with this performance, you don't need to look at the other channels, right? So but why is that? This is because the switching between branches will introduce discontinuities in the combined signal. So if you feel that the quality is okay, you don't need to look at the other branches. So two strategies are usually used. One is the switch and examine strategy, that is, you switch and then examine. And the other is switch and then you stay on that, right? Switch and examine, or switch and stay. First of all, you switch and then you examine, and if you feel that the quality is okay, you stay on that. You don't need to move on to the other branch. The correlation between branches will always reduce the diversity gain, right? Why? Because we want all of the branches to have minimum possible correlation. So the correlation will always reduce the diversity gain. So the more they are uncorrelated, the more we have diversity gain. So the effect of the correlation can be approximately modeled by introducing equivalent average SNR. We will not go into details of this mathematics, but this is very important that we need to know that the corresponding correlation between the branches should be as less as possible. Okay, so the diversity is used to provide the receiver with the several replicas of the same signal. Diversity techniques are used to improve the performance of the radio channel without any increase in the transmitted power. As high the received signal replicas are decorrelated as much as the diversity gain. As far as diversity combining techniques are concerned, the maximal ratio combining outperforms the selection combining, and the equal combining gain combining performs very close to the maximal ratio combining. Unlike the maximal ratio combining, the estimate of the channel gain is not required in equal gain combining because all of the branches are co-phased. So you don't need to estimate the channel gain in that case. Among the different combining techniques, maximal ratio combining has the best performance, but it has the highest complexity, and selection combining has the lowest performance, but it has the least complexity. So if you are okay with a certain threshold of performance, but you don't want to compromise on the complexity, then selection combining is fine. But if you want, or if you are able to bear the complexity or the cost of your processing, then obviously maximal ratio combining is the best techniques of all possible techniques that you have studied. So we will end the topic of diversity combining techniques over here. Thank you.